On January 21, 1968, North Vietnamese artillery batteries launched a sustained bombardment against Khe Sanh combat base in Quang Tri province. The shelling continued for 77 consecutive days, delivering an estimated 150,000 rounds against marine positions fortified with sandbags and corrugated steel. Intelligence officers at Military Assistance Command Vietnam headquarters in Saigon confronted a tactical paradox that defied every assessment of enemy logistics capabilities. The siege required North Vietnamese forces to maintain artillery ammunition stockpiles exceeding 10,000 tons within striking distance of a target subjected to continuous B-52 bombardment and tactical airstrikes numbering more than 24,000 sorties. Aerial reconnaissance detected no surface storage facilities. Ground patrols found no ammunition dumps, yet the barrage never stopped. The explanation emerged from tunnels beneath the demilitarized zone. American commanders had consistently underestimated the scale and sophistication of underground infrastructure supporting communist military operations. Initial intelligence assessments characterized Vietcong tunnel networks as crude shelters dug by peasant farmers using agricultural implements. The presumption reflected a broader technological arrogance that dominated Pentagon planning throughout the mid-1960s. If enemy forces operated from underground positions, American air power would render those positions irrelevant through sustained bombing campaigns designed to collapse tunnel systems and interdict supply routes. Operation Rolling Thunder alone delivered more than 643,000 tons of ordnance against North Vietnamese targets between March 1965 and November 1968. Defense Secretary Robert McNamara authorized expenditures exceeding $900 million annually to maintain interdiction operations along infiltration routes collectively designated the Ho Chi Minh Trail. By August 1966, Central Intelligence Agency assessments acknowledged complete failure of aerial interdiction strategies. North Vietnamese engineering units moved an estimated 6,000 tons of supplies monthly through mountain passes in Laos and across the demilitarized zone despite 3 years of continuous bombing. The trail network expanded from approximately 1,000 kilometers in 1964 to more than 16,000 kilometers by 1967, incorporating multiple parallel routes that provided redundancy against airstrikes. Communist forces demonstrated operational capabilities that aerial reconnaissance could not explain. Artillery units repositioned heavy weapons between firing missions without leaving detectable surface traces. Infantry battalions appeared in tactical positions hundreds of kilometers from their last confirmed locations without triggering sensor networks along predicted movement corridors. Ammunition stockpiles supporting sustained combat operations materialized in areas subjected to intensive bombardment. The answer existed beneath the jungle canopy. On February 7, 1966, soldiers from the 1st Infantry Division's 1st Battalion, 28th Infantry Regiment discovered a tunnel entrance near the village of Ben Suc in the Iron Triangle region northwest of Saigon. The opening measured 60 centimeters in diameter, camouflaged beneath vegetation and secured with a wooden trapdoor reinforced with waterproofing. Initial exploration revealed a vertical shaft descending 4 meters to a horizontal passage extending in multiple directions. Tunnel rats, soldiers small enough to navigate the confined spaces, mapped a complex incorporating more than 40 kilometers of interconnected passages on 3 distinct levels. The upper level at depths between 2 and 4 meters housed living quarters, medical facilities, and weapons storage chambers. The middle level at 6 to 8 meters depth contained command centers, communications nodes, and protected workshops manufacturing improvised explosive devices. The deepest level at 10 to 12 meters provided emergency shelters designed to survive B-52 strikes and served as protected routes for movement between tactical positions. The discovery at Ben Suc shattered fundamental assumptions about enemy capabilities. Engineers examining the complex documented construction techniques requiring advanced planning and substantial labor investment. Tunnel walls exhibited deliberate architectural features including arch ceilings that distributed structural loads, ventilation shafts incorporating baffles to disperse smoke and prevent detection, and drainage systems channeling groundwater away from inhabited chambers. Storage rooms contained rice stockpiles sufficient to sustain 200 personnel for 6 months. A conference chamber measuring 4 meters by 6 meters included benches carved from packed earth and a table constructed from scavenged lumber. One passage terminated at an underground garage housing a captured M48 Patton tank repurposed as a command post, its turret removed, and the hull converted into a protected operations center complete with radio equipment and map tables. The scale of tunnel networks throughout South Vietnam became apparent as American forces expanded search operations. The Cu Kai Tunnel system northwest of Saigon incorporated more than 250 kilometers of passages connecting villages across an area exceeding 120 square kilometers. The complex included hospitals equipped with surgical facilities, armories storing crew-served weapons and ammunition, printing presses producing propaganda materials, and even theater spaces where entertainment units performed for troops rotating through the area. Australian forces operating in Phuoc Thi province documented similar infrastructure near the village of Nui Dat. British advisory teams working with South Vietnamese units discovered tunnels in the Mekong Delta, incorporating underwater entrances accessible only during low tide periods. Intelligence assessments compiled by the Advanced Research Projects Agency in May 1967 estimated more than 5,000 separate tunnel complexes existed throughout South Vietnam, with individual systems ranging from simple two-chamber shelters to multi-level installations exceeding 50 kilometers in total passage length. The inadequacy of existing detection methods became painfully clear during operations against known tunnel areas. On March 23, 1967, elements of the Australian 1st Battalion, Royal Australian Regiment deployed to clear a wooded area near Nui Dat, where intelligence sources confirmed the presence of an extensive Vietcong tunnel network. The battalion formed a skirmish line and advanced through the vegetation searching for entrance points. The operation continued for 6 days. Soldiers located tunnels only after one man was shot from a concealed fighting position. He had walked directly past a camouflaged bunker entrance without detecting it. The Australians ultimately mapped portions of the complex but withdrew without locating all passages or permanently denying enemy use of the facility. The Pentagon's response emphasized technological solutions to tactical problems that human searchers could not efficiently resolve. Secretary McNamara convened the Jason Group, an advisory panel of civilian scientists providing technical consultation on military matters, to evaluate options for detecting and interdicting enemy infiltration routes. The Jason report delivered to McNamara in August 1966 recommended creation of an electronic barrier incorporating acoustic and seismic sensors deployed along the demilitarized zone and throughout the Ho Chi Minh Trail network in Laos. The proposed system would detect enemy movement through jungle terrain that defeated visual surveillance, providing targeting data for airstrikes without requiring ground forces to occupy contested areas. Operation Igloo White commenced in September 1967 as the largest electronic surveillance program deployed during the Cold War. The U.S. Air Force procured more than 20,000 individual sensor units designated for air delivery into target areas throughout southern Laos and along infiltration corridors approaching the demilitarized zone. The Air-Delivered Seismic Intrusion Detector, officially designated ADSID, incorporated a rocket-shaped housing 40 centimeters long weighing approximately 15 kilograms. Aircraft dropped the devices from altitudes between 1,500 and 3,000 meters. An impact-triggered mechanism buried the sensor body in soil to depths between 30 and 60 centimeters, leaving only a camouflaged antenna protruding above the surface. Internal seismometers detected ground vibrations generated by personnel movement and vehicle traffic, transmitting data via UHF radio signals to orbiting relay aircraft. The Air Force deployed Beech Cu-22B Pave Eagle reconnaissance aircraft and Lockheed EC-121R Batcat airborne command posts to monitor sensor transmissions. The aircraft maintained continuous orbits above sensor fields, receiving signals and relaying data to the Infiltration Surveillance Center at Nakhon Phanom Royal Thai Air Force Base in northeastern Thailand. The ISC facility incorporated two IBM 36065 mainframe computers, among the most powerful data processing systems available in 1967, operating in climate-controlled rooms to analyze incoming sensor reports. Technicians correlated multiple sensor activations to determine probable locations of enemy forces, generating targeting coordinates transmitted to tactical air control centers. Strike aircraft including F-4 Phantom fighters and B-52 Stratofortress bombers received mission assignments directing them against detected targets, theoretically interdicting infiltration before enemy forces reached tactical areas in South Vietnam. Complementary acoustic sensors designated ACOBOY employed technology adapted from anti-submarine warfare systems. The devices incorporated sensitive microphones suspended from parachutes, deploying in jungle canopy at heights between 15 and 30 meters above ground level. The microphones detected sounds exceeding predetermined threshold levels: vehicle engines, human voices, metallic impacts from equipment being moved through vegetation. To ensure acoustic sensors registered enemy movement even when personnel maintained noise discipline, Air Force aircraft seeded monitored areas with thousands of button bomblets, small explosive devices that detonated with distinctive acoustic signatures when disturbed by footsteps or vehicle passage. The combined acoustic and seismic detection network theoretically provided complete surveillance coverage across terrain that visual reconnaissance could not penetrate. The McNamara line, as soldiers referred to the electronic barrier system, consumed approximately $1 billion annually in operational costs excluding research and development expenditures and construction of the Nakhon Phantom Control Facility. The Tet Offensive launched on January 30, 1968, and the simultaneous siege of Khe Sanh diverted sensor deployments from planned barrier positions to defensive perimeters around threatened installations. The system never achieved its intended operational capability. More significantly, it never demonstrated effectiveness against the fundamental problem it was designed to solve. North Vietnamese engineering units moved supplies through monitored areas without measurable reduction in logistics flow. Sensors transmitted thousands of alerts daily. Analysis of correlation data produced targeting assignments for airstrikes. Yet infiltration continued at increasing rates throughout 1968 and 1969. Robert Greeley, a scientist who worked on the Jason Barrier project, later documented the operational inadequacy of the sensor network. His review of combat reports identified only 3 specific occasions where sensor alerts led to visual target confirmation, successful airstrikes, and verified destruction of enemy forces. In 2 incidents, attacking aircraft reported no secondary explosions or observable damaged targets described as killed may have simply disappeared beneath jungle vegetation. The third attack targeted a motorcycle whose rider, according to the pilot's after-action report, turned around and sped off when the aircraft began its attack run. Greeley's assessment concluded that the electronic barrier represented a technical and military failure and a huge waste of money and effort. The North Vietnamese responded to sensor deployments by adjusting movement patterns, employing decoys to trigger false alerts, and physically recovering devices for technical analysis. Tunnel detection presented even greater challenges than monitoring surface infiltration routes. In December 1967, the Department of Defense Office of the Chief of Research and Development completed a staff study examining tunnel detection capabilities across Army, Navy, Air Force, and Advanced Research Projects Agency programs. The study recommended establishment of a coordinating committee to synchronize development efforts addressing tunnel detection, denial, and destruction requirements. On April 3, 1968, the first interagency conference on the tunnel problem convened at the Office of the Chief of Research and Development Facilities in Arlington, Virginia. Representatives from military services, research laboratories, and contractor organizations presented status reports on programs addressing what had emerged as one of the most technically difficult problems facing American forces in Southeast Asia, the U.S. Army Mobility Equipment Research and Development Center delivered 2 seismic tunnel detection systems to the Army Concept Team in Vietnam on March 22, 1968, with 5 additional units following on April 12. The seismic detector incorporated a 3-kilowatt peak power electrical transmitting transducer weighing approximately 25 pounds, a small receiving transducer weighing less than 1 pound, and an electronics package including a cathode ray tube display and self-contained power source weighing approximately 40 pounds. 2 operators worked in coordination, one carrying the display unit and observing the oscilloscope for tunnel-related reflections, the other systematically probing the search area with transmitting and receiving transducers positioned at intervals along the surface. Headphones enabled passive listening for underground activities including digging sounds and human voices. The seismic system demonstrated capability to detect tunnels at depths up to 10 feet in consolidated sandy or clay soils. The self-contained power source provided 8 hours of continuous operation, with an auxiliary 16-pound battery pack extending capability to 24 hours. Sounding time averaged approximately 30 seconds per measurement point. Operators conducted soundings every 3 feet along suspected areas, advancing systematically across terrain where intelligence assessments or tactical indicators suggested underground construction. The system produced distinguishable echo patterns when transmissions reflected from tunnel walls or roof structures, displaying on the oscilloscope as characteristic signal returns occurring at twice the propagation time measured from within detected tunnels. Electromagnetic tunnel detectors developed in parallel with seismic systems employed different physical principles suited to complementary operating conditions. The Mobility Equipment Research and Development Center designed an ultra-high-frequency radar system, essentially comprising a man-portable short-pulse radar transmitting into soil from positions slightly above the surface. The device generated electrical pulses with durations measured in nanoseconds, producing wideband electromagnetic radiation that propagated through Earth and reflected from underground discontinuities including tunnel voids, buried structures, and significant changes in soil composition. Return signals displayed on an oscilloscope provided operators with echo amplitude versus time data. An optional chart recorder produced permanent records of subsurface profiles, graphing echo strength versus depth versus surface position to enhance operator interpretation of underground features. The electromagnetic detector operated effectively in dry, unconsolidated soils where the seismic system performed poorly, while seismic methods worked well in wet, consolidated media where electromagnetic wave attenuation limited radar penetration. The UHF radar detector weighed approximately 20 pounds, complete with self-contained power source providing 10 hours of continuous operation. The system did not require direct soil contact, enabling faster search rates than contact-dependent seismic methods. Maximum detection depth reached 10 feet in favorable soil conditions, dry sand or sandy clay with low moisture content and minimal mineral content that would attenuate electromagnetic propagation. Two experimental prototype units underwent development through May 1968 for deployment to Vietnam following field testing at Fort Belvoir, Virginia. Australian forces demonstrated the operational effectiveness of integrated detection methods on August 14, 1968. The 1st Field Squadron, Royal Australian Engineers, deployed ground-penetrating radar systems to search an area approximately 4 kilometers south of Nui Dat, where intelligence sources indicated probable Vietcong tunnel construction. The Australian equipment incorporated radar technology adapted from geological survey applications, modified for military field use. Operators systematically scanned the target area using methodical search patterns designed to ensure complete coverage. The radar screens displayed subsurface anomalies consistent with void spaces at depths between 1 and 4 meters. Engineers marked detected locations and initiated verification procedures using hand augers and mechanical excavation equipment. The Australian operation discovered more than 30 separate tunnel entrances and underground chambers throughout the search area, installations that conventional reconnaissance and visual inspection had completely failed to detect. Subsequent exploration documented a multi-level complex incorporating living quarters, weapons storage facilities, and protected communication positions. The tunnel system connected multiple surface positions across terrain exceeding 2 square kilometers, providing Vietcong units with protected movement routes and concealed observation posts overlooking Australian patrol routes and defensive perimeters. The successful detection operation validated ground-penetrating radar as an effective method for locating underground infrastructure, though operational constraints including equipment weight, search rate limitations, and requirement for skilled operators restricted widespread deployment. North Vietnamese engineering units continued expanding tunnel networks throughout the war despite detection technology improvements, and intensified military operations against discovered complexes. Intelligence assessments compiled in 1971 documented enemy capabilities to excavate new tunnel systems using simple hand tools while operating under sustained aerial bombardment. Construction teams worked primarily during nighttime hours, removing excavated soil in small quantities distributed across wide areas to avoid creating surface evidence detectable through aerial reconnaissance. Tunnel entrances incorporated camouflage so effective that ground patrols frequently walked within meters of openings without visual detection. Booby traps and defensive fighting positions protected discovered entrances, forcing American and Allied forces to commit substantial resources clearing individual complexes while enemy engineers constructed replacement facilities in adjacent areas. The tunnel destruction problem proved nearly as difficult as detection. The U.S. Army initially employed acetylene gas charges designated tunnel destruction kits, comprising bottles of acetylene and oxygen that tunnel rats carried into complexes, opened in underground chambers, and detonated using timed fuses or electrical initiators. The resulting explosions generated blast overpressures theoretically sufficient to collapse tunnels with overburdens. The depth of soil between tunnel roofs and the surface, up to 3 meters. Field testing demonstrated that acetylene charges destroyed shallow tunnels effectively, but failed against deeper installations, where overburdened mass absorbed blast energy without structural failure. Studies conducted by the U.S. Bureau of Mines confirmed inherent limitations in chemical energy available from hydrocarbon fuels, indicating that gaseous explosives could not generate sufficient force to collapse tunnels at depths exceeding 2 to 3 meters. Picatinny Arsenal developed the Liquid Explosive Tunnel Destruction System, designated LETUDS, employing condensed-phase explosives to achieve greater destructive effect. The system incorporated lay-flat plastic tubing deployed into tunnels by personnel using a drag pack, a dispensing device worn on the operator's stomach or back that paid out tubing as tunnel rats crawled through passages. After deploying tubing through the target complex, operators filled the tubes with PLX liquid explosive comprising 95% nitromethane and 5% ethylene diamine, pumped from shipping containers using portable equipment. A demonstration at Paris, Pennsylvania in July 1967 successfully destroyed 1,000 feet of tunnel with 10 feet of overburden. The Army shipped 30 LETUDS systems to Vietnam in June 1968, accompanied by a demonstration team providing technical training. The Vietnam tunnel warfare experience informed American military planning for subsequent conflicts, where adversaries might employ underground infrastructure. The Defense Advanced Research Projects Agency sponsored continuing research through the 1970s and 1980s, examining advanced detection technologies including trace gas analysis, detecting chemical signatures of human occupation including carbon dioxide, methane, and volatile organic compounds emitted through soil from underground chambers. Researchers investigated electromagnetic scattering measurements to identify subsurface anomalies, evaluation of ground wave propagation disruptions caused by tunnel voids, and soil disturbance indicators including argon detection and ecological effects from vegetation stress. The U.S. Army Engineer Research and Development Center developed the Rapid Reaction Tunnel Detection System, designated ADSID, combining ground-penetrating radar with electromagnetic induction sensors and acoustic detection capabilities. The integrated system provided superior performance compared to single-mode detection technologies, reducing false alarm rates and enhancing target discrimination. ADSID transmitted data remotely to analysts viewing graphical displays that enhanced underground feature interpretation. The system required only 1 day of operator training, addressing a critical limitation of earlier systems that demanded extensive technical expertise and field experience for effective employment. Field deployment began in 2014 with continual software refinement to detect tunnels at increasing depths and identify underground infrastructure signatures, including electrical cables and communications equipment. North Korea's extensive tunnel construction beneath the Korean Demilitarized Zone demonstrated that underground warfare tactics remained relevant decades after Vietnam. South Korean forces discovered the first infiltration tunnel on November 15, 1974, following detection of underground explosions during excavation operations. The tunnel originated north of the military demarcation line, penetrating 1,100 meters into South Korean territory at depths between 50 and 160 meters below the surface. The passage measured approximately 2 meters high by 2 meters wide, sufficient to permit movement of light vehicles and rapid infiltration by infantry forces. Electrical lighting, rail tracks for ore cart transportation, and ventilation systems incorporating multiple shafts indicated sophisticated engineering and substantial construction effort. South Korean and American forces located 3 additional major infiltration tunnels through 1990 using detection methods including seismic monitoring networks, analysis of refugee reports describing construction activities, and systematic investigation of geological features favoring tunnel development. The second tunnel, discovered on March 19, 1975, extended 3,500 meters from North Korean territory, with 1,300 meters penetrating south of the military demarcation line at depths between 50 and 160 meters. The third tunnel, found on October 17, 1978, ran 1,635 meters, with approximately 435 meters extending into South Korean territory at depths near 150 meters. The fourth tunnel, detected on March 3, 1990, measured 2,052 meters total length, with 1,200 meters crossing beneath the demarcation line at depths between 145 and 160 meters. Intelligence assessments suggest additional undetected tunnels remain operational, potentially numbering more than 20 separate infiltration routes. General Vincent Brooks, commander of United Nations Command, Combined Forces Command, and United States Forces Korea, described during congressional testimony the intelligence infrastructure monitoring North Korean military activities. The intelligence, surveillance, and reconnaissance architecture provides what Brooks characterized as deep look ISR and moving target indicators, providing continuous tracking capabilities and penetrating coverage of all military movements above the military demarcation line. Ground-based seismic networks detect underground activities, including possible tunnel construction. Satellite reconnaissance and signals intelligence systems monitor surface indicators of subsurface installations. Yet the terrain along the demilitarized zone, mountainous geography with extensive rock formations providing structural support for deep tunnels, favors defensive underground construction that detection technology struggles to locate comprehensively. The legacy of Vietnam-era tunnel detection research extends to current military operations and homeland security applications. United States forces deployed ADSID systems to Afghanistan and Iraq, where insurgent forces employed increasingly sophisticated tunnel networks at greater depths than Vietcong installations. Combat engineers reported the systems proved effective in field conditions, with ease of use and data display capabilities enabling successful tunnel location during counterinsurgency operations. The Department of Homeland Security adopted ground-penetrating radar technology for border security applications, detecting cross-border tunnels used for smuggling operations. Allied military forces, including Israeli Defense Forces operating against tunnel infrastructure in Gaza, integrated similar detection systems into their operational capabilities. The technological challenge that confronted American forces in Vietnam, locating and neutralizing enemy tunnel complexes that provided protected infrastructure supporting sustained military operations, demonstrated fundamental limitations in surveillance systems dependent on detection of surface signatures. Adversaries operating underground could defeat billion-dollar sensor networks and aerial reconnaissance programs through labor-intensive construction employing minimal technology. The North Vietnamese moved 6,000 tons of supplies monthly through monitored areas, despite the most sophisticated electronic surveillance system ever deployed. They sustained combat operations from tunnel complexes that survived 3 years of strategic bombing, delivering more than 600,000 tons of ordnance. The detection technologies developed in response, seismic systems, electromagnetic radar, integrated sensor suites, provided capabilities that eventually located underground installations, but never achieved the decisive operational advantage that Pentagon planners anticipated technology would deliver. The confidence that advanced surveillance systems would render enemy tunnel networks irrelevant collapsed in the tunnels beneath Khu Kai, in the passages under the demilitarized zone, and in the underground complexes that Australian engineers discovered only after systematic employment of ground-penetrating radar revealed what visual reconnaissance could not detect. The McNamara line consumed $1 billion annually and failed to interdict infiltration. The Jason scientists delivered sophisticated sensor networks that North Vietnamese troops defeated by walking quietly and carrying supplies at night. The lesson emerged clearly in declassified after-action reports and technical assessments compiled by researchers who worked on detection programs. Adversaries willing to invest labor in underground construction could create infrastructure that the most advanced technology of the era struggled to locate and could not efficiently destroy. That tactical reality, learned at enormous cost in Vietnam, continues to shape military planning confronting adversaries who go underground.